This is a revision video for the 10th physical chemistry topic in AQA A-level chemistry. In this video we're going to look at the equilibrium constant Kp, which is used in place of Kc for systems where partial pressure is easier to calculate than concentration. If you do need a refresher about equilibria and Le Chatelier's principle in general, then it's best to look back at the introductory videos for Unit 6. But we'll quickly remind ourselves of one or two things here before we go on to Kp. So in a chemical reaction, the reactants, here represented as A and B, react together to form the products, C and D. And if a reaction is reversible and those products are able to react together to turn back into the reactants, then we show this with this reversible reaction arrow. When a reversible reaction takes place in a closed system, meaning that no energy and no matter can be added in or taken away, then eventually the system will reach a point called equilibrium. At equilibrium, the forward and the reverse reactions are both still happening, and they're happening at the same rate or the same speed. So although reactants are still turning into products, that's happening at the same rate that products are turning back into reactants. And that means that overall, the concentration of the reactants and the products is unchanging. We can identify this on a graph like this one on the left by looking for the point where the two bits of the graph both plateau, because the concentrations aren't changing anymore. Crucially, as you'll see from this graph, they're not necessarily the same as each other. In fact, they very rarely are. And the whole point of equilibrium chemistry is to figure out where the equilibrium lies, and if we're talking about industrial chemistry, how to push it as far to the side with the product that we want to make as possible. As part of AS chemistry, you learned how to construct an equilibrium constant called Kc. This allows you to identify mathematically whether the equilibrium for a particular reaction lies to the right if Kc is larger than 1, or to the left if it's less than 1. Kc requires you to have concentrations for each component in the reaction, so it's easy to construct for solutions and a little trickier to use for gases, although you can, provided you have volumes or a reaction with the same number of moles on the left and right side of the equation. The equilibrium constant Kp serves the exact same function as the equilibrium constant Kc. It tells you what the position of equilibrium is and whether it lies further to the right, making more products, or further to the left, having more reactants in the system. The difference is that it's for systems in which the reactants and products are gases, rather than something where it's easy to calculate a concentration. So because mathematically these two constants are equivalent to each other, they're constructed in very, very similar ways. You'll recognise from writing equilibrium constants for Kc that again we've got the products on the top of the fraction and the reactants on the bottom. And again you'll recognise from Kc expressions that where you've got more than 1 mole of a particular reactant or product, then we show this with indices. So you have a power, so for instance I've got 2 moles of B and therefore I've got the partial pressure of B squared. The big difference is that with Kp as opposed to Kc, we're using partial pressure rather than concentration. And so it's really important that we don't use square brackets, because square brackets show you're talking about concentration, and here you're not. In actual fact, the brackets are kind of optional, and the AQA mark schemes in the last few years have used both brackets and without brackets, so it might just be easier to remember to never use brackets with partial pressure. It's also kind of optional whether you want to have pp for partial pressure or just a single p. Both methods can be used. So here's an opportunity to pause and check that you haven't forgotten how to write an expression for an equilibrium constant, and also check that you've taken that on board about how Kp will look slightly different to Kc. So pause the video, write down an expression for Kp for these 5 reactions, and then unpause to check that you've got these right. So with a little bit of luck, for the first question you've got something that looks like this. We've got the sulfur trioxide on the top of the fraction and sulfur dioxide and oxygen on the bottom of the fraction, and both the sulfur trioxide and the sulfur dioxide are squared because there are 2 moles of each of those in the equation. Then for the Haber process, we've got something that looks like this, with your ammonia on top and your nitrogen and hydrogen on the bottom. Then for making hydrogen iodide, we've got something that looks like this. So your hydrogen iodide is squared because there are 2 moles of that, but only 1 mole each of the hydrogen and the iodine. And then for number 4, you've got something that looks like this. And for number 5, we've got this. So now you can write an expression for Kp. we haven't actually talked about what partial pressures are yet, and we are going to get to that. But first, let's do a little bit of practice substituting in some values to calculate a value for Kp. So let's say that for this particular reversible reaction, the partial pressures of the reactants and products are 10 kilopascals of A, 15 of B, 30 of C, and 45 of D. So to work out my value for Kp, I would need to substitute each of these in the right place. So we're going to have 30 cubed, because that's the partial pressure of C, times by 45, because that's the partial pressure of D, and then that whole lot divided by 10 for the partial pressure of A, multiplied by 15 squared for B. And that gives me a final answer of 54. Just like Kc, Kp doesn't have one particular set of units. You need to work out what the units are by cancelling out the numerator and denominator of your Kp fraction expression. Now this is made slightly more complicated by the fact that your partial pressures could be given in a bunch of different ways, although they will just give you one way for the whole question usually. So whereas with Kc we'd have moles per decimetre cubed, for Kp you could either have kilopascals, pascals, or atmospheres. Here, all of our partial pressures were given in kilopascals. So the top of my fraction corresponds to 4 lots of kilopascals multiplied by each other, and the bottom of my fraction has 3 sets of kilopascals. So these ones cancel out, these ones cancel out, and these ones cancel out. And that means that for this particular Kp expression, my units are going to be kilopascals. Here are the same 5 reversible reactions that you met before. Pause the video and for each one write down what the units for Kp will be. So for question 1, there is 1 more mole of gas on the left hand side of the equation than the right hand side, and so I'm going to end up with kilopascals to the minus 1. In question 2, I've got 2 more moles on the left hand side than the right, so it's going to be kilopascals to the minus 2. For question 3, the number of moles on the left and right of the equation is the same, they balance out, and so all of the units cancel, and in fact Kp for this reaction will have no units. For question 4, there's 1 more mole in the products than the reactants, so the units will be kilopascals. And for number 5, we've got 2 more moles in the reactants than the products, so the answer will be kilopascals to the minus 2. We've said that to calculate Kp you need something called partial pressures, but we haven't actually explained what those are yet, so let's do that now. You've known since your GCSEs that 1 mole of gas under standard conditions takes up 24 decimetres cubed. And since year 12 you've used the ideal gas laws, so you've got this idea that the identity of a gas doesn't affect the amount of pressure that it exerts. So that means if we know the total pressure of a gas mixture, and we know what proportion of the mixture each gas is, we can assign a partial pressure just to that gas, to say if we took that gas out of a mixture and we put it in a box on its own, what would the pressure there be? Let's take a look at a simple graphical example to explain this. Here I have a box containing 10 gas particles. 5 out of 10 are red, 2 out of 10 are blue, and 3 out of 10 are green. We can refer to these fractions as the mole fractions. It tells us what fraction of all the moles are that gas. And they're going to add up to be 1, because they have to add up to be 100%. Now, if I know that in total the pressure in that box is 150 kilopascals, I can do a quick multiplication to work out what the partial pressure for each gas is. So that 5 out of 10 red gas particles, that's exerting a pressure of 75 kilopascals. And the 2 out of 10 blue gas particles, well, they're exerting a partial pressure of 30, and the green is exerting a partial pressure of 45. And again, if I add up all of those partial pressures, I get the same total pressure that I started with. These are the numbers that we're going to put into our Kp expression. So here are 3 systems where you could calculate a Kp expression. For each one, you're given the total pressure in either atmospheres, pascals, or kilopascals, and you're given part of the mole fraction. You'll need to work out what the mole fraction for the final reactant or product is by working out what's missing, so doing 1 take away the other mole fractions. Then you need to work out the partial pressure for each gas by multiplying by the total pressure. Pause the video and then press play when you're ready to check your answers. So in system number 1, we've got nitrogen as a 7th, hydrogen as 2/7, and therefore ammonia will be 4/7. If we multiply each one of those mole fractions by 5, we get 0.71 atmospheres, 1.43 atmospheres, and 2.86 atmospheres. In system number 2, we've got 25,000 pascals for hydrogen, 50,000 pascals for iodine, and 125,000 pascals for hydrogen iodide. And then in system number 3, we've got 2/5 carbon monoxide and 1/5 hydrogen, so that means that there must be 2/5 methanol. And if we multiply each of those by 120, we get 48 kilopascals of carbon monoxide, 24 kilopascals of hydrogen, and 48 kilopascals of methanol. Now, of course, nothing is ever quite this simple in A-level chemistry, although KP is quite unusual in that you do occasionally get standalone questions that literally just ask you to work out the mole fraction or the partial pressure. But more commonly, you'll meet questions where you need to use your Unit 6 Le Chatelier knowledge to work out the final proportion of gases at equilibrium, and then go on to write a KP expression or complete calculations. The easiest way to work out that final mixture of gases is to construct an ICE table, where I stands for the initial moles, C stands for the change in moles, and E stands for the end moles or the equilibrium moles. Here's a fairly typical exam question. 2.5 moles of sulfur dioxide and 3.0 moles of oxygen are put into a sealed vessel. In other words, this is a closed system and it is going to reach equilibrium. At equilibrium, the mixture contains 1.5 moles of sulfur dioxide. Total pressure is 100 kilopascals. Calculate Kp. So we've been given some information about sulfur dioxide. We know where it started and we know where it finished, and therefore we can work out what the change is, and that's going to be key to unlocking the rest of this question. Here's my ICE table. So I've got all of the different components of this reaction at the top, and then I've got my initial, my change, and my end or equilibrium. So from the question, I know that there are 2.5 moles of sulfur dioxide at the start and 3.0 moles of oxygen, and they haven't said anything about the sulfur trioxide, so I assume that there isn't any at all. Now, at the end of the reaction, there is only 1.5 moles of sulfur dioxide left, and that's a change of 1 mole. Now, looking at my equation, I can see that for every 2 moles of sulfur dioxide that are used, there will only be 1 mole of oxygen used. So, therefore, I can say that my oxygen is going to go down by 0.5. And for every 2 moles of sulfur dioxide, there are 2 moles of sulfur trioxide. So if my sulfur dioxide is going down by 1, my sulfur trioxide will go up by 1. So that's going to leave me with a final moles of oxygen of 2.5 and moles of sulfur trioxide of 1.0. The number of moles on its own isn't enough to work out Kp. I need the partial pressure, and to work out that I need the mole fraction. So firstly, I'm going to add up the total number of moles in this system at equilibrium, which is 5. And now I can use this to write a mole fraction for each reactant or product. So 1.5 divided by 5 is 0.3. And you'll see I am converting those into decimals, which is kind of the dumb thing, even though we call it a mole fraction. Then 2.5 out of 5 is 0.5, and 1 out of 5 is 0.2. And then we said that the pressure for the entire system was 100 kilopascals. So I multiply each of these by 100. So I get 30 kilopascals, 50 kilopascals, and 20 kilopascals. And if at this point I wanted to check, I could add all those up, and yes, they do still come to 100, which they should. So now I write an expression for Kp. As usual, I've got my products on the top and my reactants on the bottom, and I'm using those powers to show that there are 2 moles of sulfur dioxide and 2 moles of sulfur trioxide, and then I can substitute in my numbers. So 20 squared divided by 30 squared times 50, and that gives me an answer of 22. And then, as per usual, I need to work out what the units will be. So the 2 partial pressures on the top are cancelled out by 2 on the bottom, and that leaves me with just 1 partial pressure on the bottom. So in other words, 1 over kilopascals, so my units will be kilopascals to the minus 1. Here's another example of the same type for you to have a go at. So pause the video, work out a value and units for Kp, and then press play when you're ready to check your working. At the start of the reaction, there are 3 moles of hydrogen and 2 of iodine, and since the question doesn't tell us there's any hydrogen iodide, we assume that it's 0. By the end of the reaction, there's only 0.5 moles of iodine left, so that's a change of 1.5. Since there's no coefficient for hydrogen or iodine in the symbol equation, that means that hydrogen will be used at the same rate as iodine, so we also lose 1.5 moles of hydrogen. but there's a 2 in front of the hydrogen iodide, so we're going to make twice as many moles of hydrogen iodide as we've lost of iodine, in other words, plus 3.0. So at equilibrium, there's 1.5 moles of hydrogen left, and there's 3 moles of hydrogen iodide. Now to work out the partial pressures, we're going to add up all of those moles and get a total of 5, and then we work out a mole fraction, so 1.5 divided by 5 is 0.3, and so on and so forth. If we add all of those up, we get a total of 1, which is good and is right. Now for the pressure, we're going to multiply it by the total pressure, which was 1.2 atmospheres, and if we do 1.2 multiplied by 0.3, we get 0.36 atmospheres, 0.12 atmospheres of iodine, and 0.72 atmospheres of hydrogen iodide. Our expression for Kp looks a little like this, and if we substitute in those numbers, we get 0.72 squared divided by 0.36 times 0.12. That comes out with an answer of 12. In other words, equilibrium lies to the right and there's more hydrogen iodide than there is of the reactants. And because we've got 2 moles on the left of the equation and 2 moles on the right of the equation, those units are all going to cancel out, and this Kp expression has no units. Thank you very much for watching, and don't forget to like and subscribe so you don't miss the next video, which is about the effect of changing the pressure, the temperature and the catalyst on both the position of equilibrium and the value of Kp.